Welcome back to the Deep Dive. We have a fascinating set of papers on the desk today, and I have to say, this one feels different.
Oh, so?
Usually when we talk about advancements in AI, we're talking about size. Bigger models, more data, these massive data centers. It's really an arms race for volume.
That's been the standard narrative for years,
Yeah.
yes. The whole scale is all you need, philosophy.
Exactly. But the research we are diving into today, specifically a paper titled AirRAG from a research team at Alibaba Group, is kind of flipping that narrative on its head.
It really is.
They aren't arguing for a bigger brain. They're arguing for a slower, more deliberate brain. They're talking about a fundamental shift in the methodology of how a machine thinks.
And that distinction is absolutely critical. We aren't just looking at a chatbot that has, memorized more facts from the internet. We're looking at an architecture that allows an AI to stop, to plan, to deliberate, and even to backtrack before it gives you an answer.
So it's moving from a pure reflex to an actual reasoning process.
That's the perfect way to put it. It's a move from reflex to reason.
Which, let's be honest, is something a lot of us humans struggle with too.
Yeah.
That impulse to just blurt out the first thing that comes to mind.
Well, yeah. We all have that, so let's set the stage.
The topic is AirRAG. The acronym, and it's a mouthful, stands for Activating Intrinsic Reasoning for Retrieval-Augmented Generation via Tree-Based Search.
Quite a mouthful, yeah. But every one of those words is doing some heavy lifting.
It is, and our mission for today is to unpack the methodology behind this. We really want to understand the mechanics. We're not just asking what does it do, we're asking how does it think? And maybe more importantly, why does the old way of thinking fail so badly on certain problems?
To really appreciate the solution, you have to get a deep feel for the problem.
Yeah.
And the problem is something the paper implicitly calls the chain trap.
Let's start right there then. Section 1 of our roadmap, the problem. I think most of our listeners are familiar with the basic concept of RAG, Retrieval-Augmented Generation.
For sure. It's the standard way most businesses are using AI right now.
You ask a question, the AI goes and looks up a document from a database, and then it answers you based on what it found. Simple.
Right. Think of standard AirRAG as like an open book test. You ask the AI, what is our company's policy on remote work? The AI doesn't know that off the top of its head. It wasn't trained on your internal HR docs.
Of course not.
So step 1, it searches your company's knowledge base. Step 2, it finds the remote work policy PDF. Step 3, it reads that PDF and summarizes the key points for you.
Simple. Linear. And for that kind of question, very effective.
It's very effective for simple retrieval, absolutely. If the answer is written clearly on page 5 of the handbook, standard AirRAG is a winner. But the cracks, they start to show, and show very quickly when you ask a complex question.
A question that requires multiple steps of reasoning. The paper calls them multi-hop queries.
Exactly. Multi-hop queries are the bane of standard AirRAG's existence.
Can you give us a concrete example of a multi-hop query where the simple standard AirRAG just completely falls apart?
Okay, let's take a historical example. Suppose you ask the AI, who was the Prime Minister of the UK when the first Harry Potter book was published?
Okay, so right away, my brain breaks that down. Hop 1, I need to find the publication date of the first Harry Potter book.
Right.
Hop 2, I need to check who was Prime Minister on that specific date. It's 2 distinct lookups.
Exactly. Now, to solve this, developers came up with something called iterative RAG. It's a slightly smarter version designed to handle these chains. It does step 1, gets an answer, and then it's supposed to use that answer to perform step 2.
That sounds logical. I mean, that's how I would solve it. So where's the trap? Why doesn't that just work?
The trap is in the linearity. It's a single, incredibly fragile chain of thought. Let's play out the scenario. In step 1, the AI searches for Harry Potter first book publication date.
Okay.
But, search engines can be messy. Let's say the top result, for whatever reason, is about the movie. The AI grabs the release date of the movie 2001 instead of the book, which was actually published in 1997.
So right at the first hop, it's already got bad data.
It has critically bad data. And here's the trap. It now takes that bad data, the year 2001, and it locks it in. It commits to it completely.
It has no reason to doubt it.
None whatsoever. It moves to step 2 and performs a new search. UK Prime Minister in 2001. It finds Tony Blair. And then it comes back to you with a very confident, very well-written, and completely wrong answer.
Because the correct answer in 1997 could have been John Major or Tony Blair, depending on the exact month of publication.
Exactly. But the system has no way to know it made a mistake. This is what the paper calls the single solution space issue. Once it makes a decision in step one, it can't undo it. It can't explore an alternative.
It's like walking a tightrope without a safety net. If you make one slip early on, you just fall. But the AI keeps walking on thin air, hallucinating that it's still on the rope.
That's a great way to think about it. It lacks any form of skepticism. It doesn't have a mechanism to pause and think, wait a minute, 2001 seems a little late for the book, let me double check that. Or maybe I should search for Philosopher's Stone release date instead.
It's purely reactive. It sees a query, it executes a search, it sees a result, it generates text. The paper frames this as System 1 thinking.
Right. Fast, instinctive, and highly prone to error on any task that requires complexity or nuance.
And the really core argument in this paper is that this isn't because the large language models themselves are stupid. It's because the structure we put them in, this rigid linear chain, actively stifles their intelligence.
That's the heart of it. The authors believe that these LLMs have intrinsic reasoning capabilities. They have the latent ability to plan, to doubt, to verify. But standard AirRAG frameworks just don't give them the tools or the opportunity to use those muscles. They're forced into this reactive loop.
So enter AirRAG. This is where we shift from the problem to the high-level approach. The paper proposes moving from a chain to a tree.
This is the fundamental methodological shift. It's moving from a simple linear process to a complex branching process.
I want to dig into the intuition here because it's really powerful. The paper uses the analogy of strategy games like chess or Go to explain the methodology.
And it's a perfect way to grasp the core concept. Think about how a chess grandmaster plays. They don't just look at the board and immediately make the first move that pops into their head.
No, of course not. They sit there for 20 minutes sometimes, just staring at the pieces, looking like they're doing nothing.
But they are doing something. They are simulating. They're thinking, okay, if I move my knight to this square, my opponent has 3 likely responses. They could move their bishop here. But if they do that, I can counter with my queen. Okay, let's rewind. What if instead I move my pawn forward?
They're building a tree of possibilities in their mind. They're exploring different futures, evaluating which one looks like a win, and then, only then, do they actually make their move on the board.
And AirRAG is applying that exact same logic to the process of answering a question. It's building a decision tree.
So instead of just generating the next word or the next search query, AirRAG uses an algorithm called Monte Carlo Tree Search, or MCTS, to explore the entire solution space.
Yes. It simulates the conversation with itself. It asks, okay, what if I search for this exact term? What kind of results might I get? Does that path look promising? Maybe not. What if I try rewriting the user's question first? Let's explore that branch.
It's the difference between reaction and deliberation.
100%. It's building in a system-to-thinking process for the AI. Slow, deliberate, analytical, and much more robust.
Okay, so that's the high-level philosophy.
Yeah.
But we promised the listeners a deep dive into the methodology, the nuts and bolts. We need to look at the engine that drives this. To play a game of chess, you need to know what the legal moves are, right?
Yeah.
A pawn can't just jump across the board.
Right. You need a defined set of possible actions.
And the authors of this paper define a specific action space.
This is a crucial part of the paper. To build this tree of possibilities, the AI needs a menu of options at every node, at every decision point. It needs a list of reasoning actions. And the authors designed 5 very specific, very human-like actions that the model can choose from at any point in the process.
Let's walk through these 5 because they really do illustrate how the system mimics a human reasoning process. Action number 1 is A, which stands for system analysis.
This is the planner. And this is, in my opinion, one of the most important innovations here. This is a distinct step where the model is prompted to just pause and analyze the problem before it even tries to search for an answer.
Why is that a separate action? Why not just build that into the main thought process?
Because making it an explicit selectable action allows the system to value it. In a tree search, the system can learn that for certain types of questions, choosing the say action first leads to a much higher success rate. It's about recognizing that planning itself is a valuable move.
So when it chooses say, what does the output look like?
It decomposes the problem. For that Harry Potter question, the say action might output something like task analysis. This is a multi-hop query with 2 main components. Step 1, identify the publication date of the book Harry Potter and the Philosopher's Stone. Step 2, identify the UK Prime Minister on the date found in Step 1, dependency. The success of step 2 is entirely dependent on the accuracy of step 1.
Wow. So it's literally building a dependency graph. It's creating a roadmap before it even starts driving.
Exactly. And remember, this is happening inside a tree. So in one branch, it might create that detailed plan. In another branch, it might try a different, simpler plan. And the system can then simulate which of these plans is more likely to work.
That's a huge departure from the old way. Okay, action number 2, DA or direct answer.
This is the internal memory action. The idea here is that sometimes you don't need to look things up in an external document.
Right. If I ask what is the capital of France, you just know it's Paris. You don't need to go search Wikipedia.
You just know it. The direct answer action allows the model to use its own parametric knowledge, all the information that was encoded into its neural weights during training, to answer the question immediately.
But why include this in our AirRAG system? Isn't the entire point of AirRAG to look things up and avoid relying on the model's memory, which can be faulty?
It is, but there are 2 good reasons. The first is efficiency. If the answer is something incredibly common and factual, searching for it is a waste of time and computational resources. The second reason is context. Sometimes the answer isn't in a document, it's a piece of common sense logic.
But isn't that incredibly risky? That's exactly how hallucinations happen, when the model confidently states something from its memory that's just plain wrong.
It is risky, absolutely. But here's the magic of the tree structure. This is just one branch of the tree. The system might try a direct answer in branch A, but at the same time, it's trying a retrieval answer in branch B.
Ah, I see.
If the direct answer from its memory, Paris, later contradicts the search results from its retrieval, actually, the capital is Lyon, which is wrong. The system will see that discrepancy. The path that relied on the faulty memory will get a low score, and the system will discard it. It creates a system of checks and balances.
So it's not committing to its memory, it's just proposing it as one possibility among many.
Exactly. It's one hypothesis to be tested.
Okay, that makes sense. Action number 3 is RA, or Retrieval-Answer. This one seems more straightforward.
This is the bread and butter of any AirRAG system. This is the researcher. The model decides it needs external knowledge, so it generates the specific search query, sends that query to the external database or search engine, and gets back the relevant documents.
So that's the core lookup function.
Yes. But action number 4 is where I think the real intelligence amplification comes in. QT, or query transformation, the refiner, or as I like to think of it, the translator.
A translator? Why a translator?
Because you and I, and all humans, are notoriously bad at asking precise questions, especially to a computer. We use slang, we're ambiguous, we assume a ton of shared context. If you just take the user's raw text and plug it into a search engine, you often get garbage results.
The old garbage in, garbage out problem.
Precisely. The query transformation action is a moment where the model can pause and say, okay, the user asked X, but I know that to find the actual answer, I need to search for Y, Z, and maybe even alpha. It translates the user's intent into an effective search strategy.
So it's not just searching, it's rewriting the prompt to be better for the search tool.
It rewrites it, it breaks it down, it expands it. For example, if the user asks a really long, convoluted question with multiple parts, the QT action might extract 3 or 4 precise keywords to search for separately.
Can you give an example?
Sure. Let's say the user asks, hey, what are the financial implications of that new Q3 marketing campaign in Europe, especially considering the recent supply chain disruptions we talked about last week?
A standard search for that whole sentence would be useless.
Completely useless. The QT action would break it down into multiple potential queries. One branch might search for Q3 Europe marketing campaign budget. Another might search for supply chain impact on European logistics. A third might try something called step-back prompting, where it generates a broader, more abstract query first, like methods for calculating marketing ROI, just to get the general context before diving into specifics.
That is incredibly useful. It's the AI admitting to itself, I don't think searching for this exact phrase is going to work. Let me try a few different angles.
And that creates huge diversity in the search results. In a standard chain, if your first query is bad, you're dead in the water. In a tree, you can have 5 different branches with 5 different variations of the search query running in parallel, and you can see which one brings back the gold.
That's powerful. Okay, and that brings us to the final action. Action number 5, essay or summary answer.
This is the synthesizer. This is the convergence point at the end of a path. This action is chosen when the model believes it has gathered all the necessary information. It takes all the intermediate steps, the plan from SA, the facts from array, the refined questions from Q2, and it weaves them all together into the final coherent response for the user.
So this is the final step in any successful branch of the tree.
Correct. It's the action that says, okay, exploration is over for this path, let's produce the final answer.
So to recap, we have the planner, SAY, the internal memory, DA, the researcher, RA, the refiner, QT, and the synthesizer, SA. These are the 5 legal moves the AI can make in its game of find the answer.
Those are the moves. Now, the real magic, the part that makes this all work, is how these moves are orchestrated by the engine. Monte Carlo Tree Search.
Right. This is section 4 of our outline, the engine. MCTS is a concept that I think scares a lot of people because it sounds very heavy on the math and computer science. But I want us to really break down the 4 steps: selection, expansion, simulation, and backpropagation conceptually. How does the AI actually use these to make its decisions?
Let's stick to that game analogy because it works perfectly. Imagine the AI is at the very beginning of the problem. It has the user's question. This is the root of the tree or a crossroads. That's where we start step 1, selection.
It has to choose which path to investigate first.
Right. It looks at all the available paths from its current position and has to decide which one looks the most promising. And to do that, it uses a specific algorithm called UCT, which stands for Upper Confidence Bound Applied to Trees.
Okay, let's not get lost in the formula. What is UCT trying to do in plain English?
In plain English, UCT is trying to balance 2 competing and very human instincts: exploitation and exploration.
The classic dilemma. Do I stick with what I know works, or do I try something new? Curiosity versus greed.
That's it exactly. Exploitation is the greed part. It says, this path, let's say the one that starts with a very specific search, has worked well in past simulations. It has a high average score. Let's keep going down this road because it's a safe bet to give us a good answer.
And exploration.
Exploration is the curiosity, it says. I haven't checked out this other path yet, the one that starts with rewriting the query. It's a bit of a long shot, it might be a total dead end, or it might be a brilliant shortcut to the perfect answer. I should probably check it out at least once, just in case.
So UCT is a mathematical way of forcing the system to not just stick to the obvious, most promising path every single time. It forces it to check the side roads every now and then.
Precisely. It prevents tunnel vision. It ensures that the system doesn't just get lucky on its first try and miss a much better solution that was just one weird search away. So the system uses UCT, it selects a node to investigate, and that brings us to step 2, expansion.
This is where the tree actually grows larger.
Yes. The system arrives at the selected node, the end of a path it's exploring, and it generates new possibilities from that point. It says, okay, from here, having just retrieved this document, I could try to summarize an answer right now, move A. Or I could perform another retrieval to get more detail, move B. Or maybe I should use query transformation to ask a follow-up question, move C.
And it adds all those new potential moves as new tiny branches to its map of the solution space.
It literally expands the tree, adding new leaves. Now comes step 3, which is the part that I still find kind of futuristic every time I think about it, simulation. This is also known as the rollout.
This is where the system doesn't just plan, it actually plays out the scenario.
It plays out the scenario, exactly. It doesn't just guess what might happen. It fast-forwards the rest of the conversation. It picks a path from the new node and just runs with it, usually making random or semi-random choices for actions until it reaches an end state.
So it's executing the actions. It's actually performing the search, reading the text, generating a draft answer in its own internal monologue.
Yes, it's simulating the future of that one path. If I choose this action, and then this action, and then this action, what answer do I end up with? It keeps going until it hits a terminal state, which usually means it has generated a final answer using the SA action, or until it hits a predefined maximum depth to stop it from going on forever. It's testing the hypothesis of that branch.
Okay, so it reaches the end of that one simulated future. It has a potential answer. But now it needs to know if it won or lost the game, right? If that path was any good.
Correct. And that is the final and most important step. Step 4, backpropagation.
The scorecard.
The scorecard. The system has to evaluate the result of that simulation. Did the answer it produced actually address the user's question? Was it coherent? Was the retrieved information relevant? Did it hallucinate?
How does it know the score? I mean, who is grading this test?
This is a really important point we need to touch on later, but typically this involves what's called a reward model. It's often another separate AI component that has been specifically trained to act as a judge. Its only job is to look at a reasoning process and a final answer and assign a numerical score to its quality.
Okay, so it gets a score. Let's say it gets an 8 out of 10. What does it do with that number?
It sends it backwards through time, in a sense. The score is sent backwards up the tree. It's backpropagated all the way to the root. It updates the value of every single decision, every node that led to that outcome.
So if a particular path led to a dead end and got a score of 1 out of 10, the system goes back and marks every turn it took to get there with a little penalty. It says, don't go this way again. It's probably a bad road.
Exactly. And if a path led to a brilliant answer and got a 10 out of 10, it goes back and boosts the probability of taking those same turns in the future. It adds a little bit of reward to each decision on that successful path.
This is the absolute key, isn't it? The system is learning the best strategy for this one specific question while it is in the process of trying to answer it.
That is the profound difference. A standard AirRAG system uses a fixed pre-programmed strategy. AirRAG adapts its strategy in real time. The MCTS process repeats this loop selection, expansion simulation, backpropagation over and over again, thousands of times, before it ever gives you an answer.
And with each loop, the scores in the tree get more and more accurate. So the exploitation part of the UCT algorithm starts to favor the paths that have consistently led to good outcomes.
You've got it. If the question is about obscure history, the tree will quickly learn that multiple, careful retrieval steps are high value. If the question is a logic puzzle, it might learn that spending a lot of time on the initial system analysis action is the key to success. It customizes its own brain for the task at hand.
But this creates a new challenge. If the AI runs, say, 1,000 simulations and builds this massive tree with 50 different main branches, it might end up with 10, 15 different potential final answers.
Correct, it will.
So how on earth does it pick the winner? This brings us to Section 5, Selection and Verification.
This is the challenge of choice. You've done all this incredible exploration of the solution space, and now you have to land the plane. The paper discusses a few mechanisms, but the most robust and intuitive one is self-consistency.
Which is basically just voting, right?
It's democracy for algorithms, yeah. Let's say the AI runs 20 simulations or 20 rollouts. In 15 of those paths, despite taking slightly different routes, maybe one used a different search query, maybe another relied on a bit of parametric memory, they all converge on the final answer, the Delaware River.
Okay.
But maybe 3 of the paths got confused and ended up with the answer, the Schuylkill River. And 2 paths went completely off the rails and hallucinated an answer like the Mississippi River.
The system sees that 15 out of 20 votes went to the Delaware River and assumes, with high confidence, that this is the correct answer.
Precisely. It relies on consensus. The underlying logic is that there are many, many ways to be wrong, but there's usually only one way to be right. If multiple independent lines of reasoning, different searches, different plans, different logical steps all point to the exact same fact, your confidence in that fact should be very high.
That makes perfect intuitive sense. It's like asking 10 different experts a question. If 9 of them give you the same answer and 1 disagrees, you're probably going to trust the 9.
Exactly. And this leads directly to a really important concept the authors discuss in the paper called inference scaling laws. This is a super hot topic in the AI world right now.
Okay, explain that for us. We're all familiar with scaling laws for training a model, bigger data, and more compute during training equals a smarter AI. What is inference scaling?
Inference scaling proposes a different idea. It says, you don't necessarily need a bigger, more expensive model to get smarter results. You just need to give the existing model more time to think at the moment you ask it a question.
So, time equals intelligence, at least at the point of inference.
In a way, yes. The paper shows that if you allow the model to run more simulations, to generate more branches, to explore deeper into the tree, to perform more of these rollouts, the accuracy of the final answer goes up, and it goes up in a surprisingly linear fashion.
So you can literally trade speed for IQ.
You can trade compute at inference time for quality. And this suggests a future where we might have different modes for AI. We might have fast AI for simple, low-stakes questions, and then slow AI for deep, complex problems.
So for a simple chatbot, you want an answer in half a second. But if you're asking an AI to, say, analyze a complex legal contract,
you might be perfectly happy to wait 60 seconds or even 5 minutes for an answer if you know that in that time, the AI has run 10,000 simulations to cross-reference every clause and verify every fact.
it validates this whole idea of test time compute. Instead of spending millions more dollars training the next generation model, you can just spend a few cents extra every time you ask your current model a hard question to let it think harder.
That's it. AirRAG is one of the first practical demonstrations that thinking longer really, really works.
I want to ground this entire methodology in a real example now. The paper includes a case study that I think just perfectly illustrates the difference between the chain failure and the tree success. It's the Bartram's covered bridge example.
Oh, this is a classic. It's in figures 13 and 14 in the paper for anyone following along. It's just a perfect example of a nested, confusing, multi-hop query designed to break simple systems.
Read the question for us exactly as it's written.
The user asks, what is the mouth of the watercourse for the body of water where Bartram's covered bridge is located?
Okay, my own brain just did a somersault trying to parse that. I'd break that down myself. Mouth of the watercourse for the body of water where the bridge is.
It's a Russian nesting doll of a question, right? To solve it, you need to 1. Find the location of Bartram's covered bridge. 2. Identify the specific body of water that runs under the bridge. 3. Find the name of the larger watercourse that body of water is a part of. 4. And finally, find the mouth or the endpoint of that watercourse. It's a 4-hop problem.
So let's put on our standard iterative RAG hat. How does that kind of model handle this disaster of a question?
It panics. It does what it's programmed to do. It grabs the first recognizable entity in the sentence, which is Bartram's covered bridge, and it searches for that.
And what does it find?
It finds a Wikipedia snippet, let's say. Something like, Bartram's covered bridge is a historic covered bridge located in Newtown Square, Pennsylvania.
Okay, that's a useful fact. It has a location. But that snippet doesn't mention the specific creek or river it's on.
Not at all. So the iterative model is now stuck. It has the fact, Pennsylvania, and the entity bridge. It might try its next iterative step and search for water under Bartram's bridge. Maybe it finds a document that mentions Goshen Road crosses the creek at the bridge.
But it doesn't explicitly name the creek?
Or maybe it does, but the AI doesn't correctly parse that Crum Creek is the proper name because the sentence structure is ambiguous. The model starts looping. Its internal state is confused. It asks itself again, where is the bridge? Pennsylvania. What water is it on? I don't know. Let me search again for the location of the bridge. It gets trapped in a useless loop, retrieving the same unhelpful documents over and over until it hits its turn limit and gives up.
It's fallen right into the chain trap. It made a bad first search, got an incomplete answer, and had no mechanism to recover or change its strategy.
Total failure. Now let's walk through the AirRAG execution of the same problem.
Okay.
AirRAG receives the query. The first thing it does in one of its primary branches is choose action 1. Say, system analysis. It pauses, it doesn't search yet, it outputs a plan.
What does the plan look like?
Something like decomposition. The user wants to find the mouth of a watercourse. This requires 2 subtasks. Subtask 1, identify the body of water that Bartram's covered bridge spans. Subtask 2, identify the mouth of that body of water.
It's isolated the variables and the dependencies right from the start.
Right. Now with that plan in mind, it enters the tree search. In one branch, it tries action 3, Retrieval-Answer. Guided by its plan, it executes a very specific search. Body of water under Bartram's covered bridge.
And because that query is much more specific than the first models, it gets a better search result.
Exactly. It finds a document that says, the bridge carries Goshen Road over Crum Creek in Delaware County.
So subtask 1 is unlocked. The body of water is Crum Creek.
Now, because this is a tree, that new crucial piece of information, Crum Creek, is passed down to the next node in the tree. The system looks at its plan and sees that subtask 1 is complete. Now it needs to execute subtask 2, find the mouth of the water. So it chooses action 4, QT, query transformation.
It refines the search.
It completely changes the search. It's not asking about the bridge anymore. That part is solved. It formulates a new, clean query, mouth of Crum Creek.
Which is a much, much easier question for any search engine to handle.
Trivial. The search engine immediately returns a result. Crum Creek is a tributary of the Delaware River.
And there's the final piece of the puzzle.
The system now has the complete, verified, logical chain. Bridge is over Crum Creek, which flows into the Delaware River. Now, at the end of the successful branch, it chooses the summary action, SA. It packages this all up and delivers the final answer. Bartram's covered bridge is located over Crum Creek. The mouth of Crum Creek is the Delaware River. Therefore, the answer is the Delaware River.
It seems so obvious and simple when you break it down like that. But the obviousness is a direct result of the planning and a structured, adaptive search process.
The structure imposed by the tree allowed it to solve and verify each step independently. And think about this. If its search for mouth of Crumb Creek had come up empty, it wouldn't have failed. It could have just backed up the tree and tried a different QT action, like searching for streams in Delaware County, PA, without having to throw away the correct fact that the bridge was on Crumb Creek.
That ability to back up and try a different path without starting from scratch, that's the game changer.
That's the robustness the tree gives you.
Okay, so we've seen the problem, the methodology, and the case study. I want to briefly touch on how this compares to other advanced models out there. The paper specifically calls out a model named AirRAG.
Right, AirRAG is a strong competitor in this space. It's another advanced iterative model that tries to decompose questions. But the paper makes a key point that AirRAG is still fundamentally too linear. It lacks the diverse and explicit action space that AirRAG has.
What do you mean by that?
AirRAG's process is usually a fixed loop of think, search, answer. It doesn't have the explicit selectable actions for high-level planning like say, or for sophisticated query rewriting like QT. It's trying to do those things implicitly, but because they aren't discrete moves the AI can choose, the system can't learn when one is more valuable than the other.
So it's like trying to build a house, but your only tool is a multi-tool. It can kind of do everything, but not as well as dedicated tools. AirRAG has a separate hammer, a saw, a grill, and a blueprint.
That's a great way to put it. That flexibility of the explicit action space allows AirRAG to handle a much more diverse range of complex questions that can trip up even other advanced models.
The authors also mention a version called AirRAG Lite. What's the compromise they're making there?
Well, this is where we have to address the big elephant in the room with this entire method. The cost.
Right. It sounds computationally expensive.
It's extremely expensive. Running MCTS and generating, say, 50 full simulations requires at least 50 times the compute of a standard single-pass query. It's not cheap to have your AI think this hard.
So AirRAG Lite is a faster, cheaper version.
It's a more streamlined version, yes. The authors did experiments where they disabled some of the more complex actions, like the explicit system analysis, SAY, or the direct answer, DA. They found that even with a simplified action space, as long as you keep the core tree search structure and the crucial query transformation action, you still get a very significant performance boost over standard iterative models.
So the takeaway is that the tree architecture itself is the real winner, even if you simplify what can happen at the nodes.
Exactly. Moving away from that brittle linear chain is the primary driver of success.
We always like to end by looking at the limitations or assumptions of any methodology. Nothing is a perfect silver bullet. What are the big assumptions the authors are making here that we need to be aware of?
There are two major ones, and they're connected. The first, and maybe the biggest, is what I call the judge capability. Remember that reward model we talked about? The one that scores the branches of the tree during backpropagation?
The teacher that's grading the AI's work in real time.
Well, this entire methodology rests on the assumption that judge is good at its job. It assumes that the model, or the separate reward model, is capable of accurately looking at a reasoning step and deciding if it was good or bad.
And if the judge is bad, if it has poor taste.
If the judge is bad, the whole system is poisoned. If the reward model hallucinates and decides that a completely irrelevant search result is actually highly useful and gives it a 10/10 score, the MCTS algorithm will start to optimize for that bad path. It will confidently and very deliberately march the whole system off a cliff.
So AirRAG is only as good as its ability to self-evaluate.
That's a huge potential bottleneck. It means you need a very capable, very well-trained model to even run the process in the first place, to act as that reliable judge.
That's the second big assumption.
The second is the compute assumption. We've touched on this, but it's worth stating clearly. This methodology assumes that spending more computational resources, more tokens, more GPU time is an acceptable trade-off to get a better answer.
Which brings us back to latency. You cannot use the full-featured version of AirRAG for a real-time voice chat application.
Absolutely not. If you ask your phone's voice assistant, what's the weather like? And it pauses for 45 seconds to build a Monte Carlo tree and run 1,000 simulations, you're going to throw your phone across the room.
So this is a methodology designed specifically for deep work. Things like scientific research, complex legal discovery, medical diagnosis, strategic planning.
Precisely. It's for any task where accuracy and thoroughness are overwhelmingly more important than speed.
Okay, before we wrap this all up, I want to circle back to the so what of this deep dive. We've geeked out on the algorithms, the trees, the actions, But what does a methodology like this really represent for the future of AI?
I think it represents a fundamental shift in focus from knowledge to process. For the last few years, the whole field has been obsessed with how much an AI knows. Has it read the whole internet? Does it know physics? Does it know history?
The encyclopedia era of AI?
The encyclopedia era, exactly. But AirRAG suggests that we are now entering the reasoning era. It's not about what the AI knows instantly. It's about the AI knowing how to figure things out. It's about giving the AI a robust process for navigating uncertainty and finding truth.
It's very biomimetic, isn't it?
Yeah.
It's copying how an expert human solves a hard problem. When I'm faced with a hard research question, I don't just guess. I make a plan. I do some initial research. I realize my initial question was flawed, so I revise it. I gather evidence. I synthesize it.
And you probably ask a colleague for a sanity check on your conclusion. That's the self-consistency voting mechanism. AirRAG is essentially giving the AI a cognitive architecture that mimics the scientific method, form a hypothesis, test it, evaluate the evidence, and iterate.
So let's summarize the key takeaways for everyone listening. The headlines from this deep dive.
Okay. Headline number 1. The chain trap is real. Standard AI systems are fragile because they think in a straight line. One small mistake early on can break the whole chain of reasoning.
Headline number 2. The tree is the solution. AirRAG uses Monte Carlo Tree Search to explore multiple possible futures at once, simulating different searches and answers before it commits to a final conclusion.
Headline number 3. A diverse action space is key. It gives the AI a flexible toolkit of 5 human-like reasoning action system analysis, direct answer, retrieval, query transformation, and summary, which allows it to adapt its strategy to the specific problem.
And headline number 4. Inference scaling is the future. We can now directly trade speed for intelligence. Letting an AI think longer by running more simulations yields measurably better answers.
That last point for me is the one to watch. The System 2 era of AI, the era of slow, deliberate reasoning machines, is just beginning.
It leaves us with a really provocative thought to end on. If thinking time at the point of inference directly equates to intelligence and accuracy, are we heading toward a world where the quality of your AI's answer depends on how long you can afford to let it think?
It seems very likely. We might see the rise of deep work agents as a service. You give an agent a complex business problem on a Friday, pay for a full weekend of compute, and it spends that time simulating millions of strategies, and then gives you the optimal, fully reasoned solution on Monday morning.
A weekend thinker. I like that. I think we could all use one of those to handle the heavy lifting.
Absolutely. The future isn't just bigger models, it's models that think harder.
Well, that wraps up our deep dive into the methodology of AirRAG. We hope you managed to avoid the rabbit holes today, or at least if you did fall into one, you now have a map of the tree to find your way back out.
It was a pleasure exploring all the branches with you.
Thanks for listening. We'll see you on the next deep dive.